Okay, in this presentation, we're going to look at calculus for random variables. So what we're doing is extracting expressions for the mean, the variance, the cumulative distribution function, etc., for a given probability distribution. Okay, so we've got a bit of work to do. The random variable x has a probability distribution f of x given as follows. K equals x squared times 1 minus x. Here, x is between 0 and 1. That's important because that gives us the limits for integration when we have to do some integration. So we got a couple of exercises here. Compute the value for k. Compute the mean and variance of x. That's a long one. Determine the cumulative distribution function f of x, and compute the probability that x lies between one standard deviation of its mean. Okay, so exercise A. So the definite integral of f of x lies between 0 and 1, and that must equal 1. Okay, so essentially what we have to do is evaluate this definite integral. The upper and lower limits of integration are 0 and 1, so we'll come back to that shortly, but we'll just concentrate on f of x. Okay, so we have the integral of kx squared times 1 minus x dx. So essentially we just re-express that as kx squared minus kx cubed. Okay, and get the integral of that. Now we can split that up into two parts. Okay, so we have kx squared and evaluate that, and evaluate for the limits 0 and 1. So kx squared becomes kx cubed divided by 3, and when we evaluate that between 0 and 1, we just get k divided by 3. Likewise, kx3, when we integrate that, we get kx to the power of 4 divided by 4, and again integrated between 0 and 1, which is k times 1 to the power of 4 divided by 4 minus k times 0 to the power of 4 divided by 4, which is just essentially k divided by 4. So essentially our integral becomes k divided by 3 minus k divided by 4. If you simplify that algebraically, you will get an answer of k divided by 12, k over 12. Now the thing about k over 12 is that value must equal to 1. So for this to equal to 1, k must equal to 12. Okay, so that's the answer to the first one done. K is equal to 12. To sum up on that one, essentially it's a definite integral that must equal 1. Okay, that's how you do exercise A. Now, what we're going to do now is calculate the mean and the variance. Okay, so we're still doing definite integrals here. We have the expected value of x, and that's the integral from 0 to 1 of x times f of x, where f of x is the probability density function. So it's similar enough to the last expression, just we have an additional expression here, x, in our integral. So it's x times f of x. We also have to calculate the variance of x, which is, we're going to use this expression here. The variance of x equals expected value of x squared minus the expected value of x to be squared. So what does that mean? Essentially what we need to do is this second definite integral, the expected value of x squared, and that is the integral from 0 to 1 of x squared times f of x dx. Okay, so essentially that's just a recap on all the building blocks that we need. So we'll crack on and get on with the median, or the mean. So the expected value of x, there we go, is x times f of x dx. Okay, so x times f of x, f of x is simplifying the expression we had previously, that is 12x squared minus 12x cubed. So our overall expression, our overall integral, becomes 12x cubed minus 12x to the power of 4. So we have to get the integral of that, okay, and evaluate it between 0 and 1. Now, this is straightforward enough. So essentially what we're going to do is take the constant term 12 outside our integral and evaluate it at the end. So x cubed, the integral of that is x to the power of 4 divided by 4. And we have x to the power of 4, and integrate that. We have x to the power of 5 divided by 5. So that's a definite integral evaluated between 0 and 1. And of course, don't forget that constant term 12. Okay? So that means I actually go into a bit of detail here trying to simplify it, but essentially what happens is, if just re-evaluated, we have 12 times, just to sort of make it easier to follow, essentially algebraically, essentially it ends up as 12 times 5 over 20 minus 4 over 20. That is 12 over 20. So the expected value is 3 over 5. Okay. I'll go into a bit more detail there, but I'll just gloss over it. Hopefully you should be able to evaluate definite integrals like that for relatively straightforward expressions. Now, the next one, the expected value of x squared. So this is building up to getting the variance of x, okay? Now, essentially what we have here is definite integral from 0 to 1. Essentially we have x squared times f of x, which is x squared times 12x squared minus 12x cubed. Simplifying that expression, we have a definite integral of 12 times x to the power 4 minus 12 times x to the power 5. Okay, so that integral evaluated from 0 to 1. Okay, now when we calculate that expression, or when we evaluate that expression, or get the integral of that expression, I should say, and apply the limits of integration, the definite integral limits, we have 12x to the power 5 divided by 5 minus 12x to the power 6 divided by 6, evaluated from 0 to 1. Now, essentially, I'm just going to give you the short answer there this time. It's worked out the same way, but essentially it will work out to be 12 divided by 12 divided by 30, okay, which works out to be 2 divided by 5, okay. Similar enough to the previous exercise, but yeah. So anyway, that's the answer there, 2 divided by 5. Okay, so now we're ready to compute the variance. Okay, so the variance of x equals the expected value of x squared minus the expected value of x to be squared. So we have 2 divided by 5 minus 3 over 5 squared. Okay, so 2 divided by 5, that is 10 over 25. 3 over 5, that is 9 divided by 25. So 10 divided by 25 minus 9 divided by 25, that is 1 over 25. So we're going to be dealing with probabilities later on. So 1 over 25, you can express that as 0.04. Likewise, 3 over 5 and 2 over 5 as 0.6 and 0.4 also, if you wish. Now, so moving on to the cumulative distribution function. Now, this one's straightforward enough. It's a definite integral. Now, essentially what we want to end up with is an expression in terms of x. So it's capital F of x, okay? So how do we go about this? Well, we just have to integrate the probability density function from the lower bound of the interval. In this case, we were told previously that the x is a variable between 0 and 1. So our lower bound there is 0. In other cases, it could be minus infinity. You're going to be told anyway, so you just have to pay attention when you're given the definition of the probability density function. But anyway, the upper bound is x. So it's the lower bound, whatever you're told, to the upper bound, x. And because we want an expression that results in an expression in terms of x, we just use a different variable here. So rather than x, we use u. So rather than having the integral of f of x dx, we're going to use u instead, so that our answer, when we evaluate it with the definite integral, will end up as x. So we use this dummy variable u instead. So it's the integral from 0 to x of 12u squared minus 12u cubed du. So that f of u du is 12u squared minus 12u cubed du. Okay? So we have an expression there. Our definite integral becomes a definite integral of 12u cubed divided by 3 minus 12u cubed divided by 4, or 12u to the power 4 divided by 4, evaluated from 0 to x. Okay, so that ends up as 12x cubed divided by 3 minus 12x to the power 4 divided by 4, and simplifying that, we end up with an expression here, 4x cubed minus 3x to the power 4. And again, just actually at the bottom there, just to reinforce the importance of that, here x is between 0 and 1. Okay, that's the lower bound of the definite integral. So there's one thing you have to remember about that, but actually it's straightforward enough. So if you're handy with definite integrals, it's just a straightforward definite integral. Now, this is a tricky enough one. Calculate the probability that x lies between one standard deviation of its mean. Okay, so we have the mean from earlier on, which is the expected value of x. Here I'm just going to call it mu, because this is sort of how we would sort of look at these sort of probability intervals. That is 0.6. The standard deviation is the square root of the variance. So sigma equals the square root of 0.04, which is 0.02. So essentially what we have to do is find out the probability of x being between mu minus sigma and mu plus sigma. Okay. Really, the notation jump there is just actually a standard about how you would carry out these sort of calculations. So it's the sort of the approach that you would, the notational approach that you take for these sort of questions. So that's why there's just a bit of a jump there between e of x becoming mu and standard deviation of x becoming sigma. Really, it's easier to look at. That's really all we have. That's all the answer. All there is to it. So essentially, what we have to do find out is a probability of x being between 0.4 and 0.8. Okay, so that's essentially the question. So we're going to use the cumulative distribution function that we've calculated previously. Okay, so the probability of x being in that interval between 0.4 and 0.8 is f of 0.8 minus f of 0.4. Now again, we have our cumulative distribution function, which is 4x cubed minus 3x to the power of 4. So we're just going to evaluate that for 0.8 and 0.4 respectively. So f of 0.8, the cumulative distribution function of 0.8, is 4 times 0.8 cubed minus 3 times 0.8 to the power of 4. That is 4 times 0.512 minus 3 times 0.4096. That is 2.048 minus 1.2288. And that should work out close to 0.8192. Okay, probably 4 decimal places is appropriate here. Anyway, similarly, the cumulative distribution of 0.4, f of 0.4 equals 4 times 0.4 cubed minus 3 times 0.4 to the power of 4. That is 4 times 0.64 minus 3 times 0.0256. So 0.256 minus 0.0768, and that is 0.1792. Okay, so essentially what we're interested in is the difference of the two numbers. That is 0.8192 minus 0.1792, that is 0.64. So the probability that x lies within one standard deviation of its mean is 0.64. And that is us done. Great.